Today, we're diving into something pretty wild, a really strange connection between a famous mathematical shape and, well, the entire universe. So let's kick things off with a shape I'm betting you've seen before. Yep, the Mandelbrot set. It's just incredibly complex, right? But what's wild is that all of this complexity comes from a super, super simple rule. And that brings us to a pretty mind-bending question. Could the blueprint for our entire universe be hiding inside this shape? I know, it sounds totally out there, but a new theory in physics is proposing just that this fractal is a powerful analogy for how our universe is put together. So yeah, let's get into it. Okay, to really get this connection, we have to understand what the Mandelbrot set actually is. Because, it's way more than just a cool-looking screensaver. It all boils down to this little formula right here. You take a number, you plug it in, you get a result. And then you take that result and plug it back into the same formula. You just keep doing that again and again and again. It's basically a mathematical feedback loop. Now, here's where it gets interesting. For any number you start with, there are really only two things that can happen. Either the results stay contained, predictable, they just kind of bounce around in a stable way, and those are the numbers inside the set. Or they just explode. They shoot off towards infinity, totally chaotic and unbounded. Those are the numbers outside the set. So that's incredibly detailed, fuzzy-looking boundary. That's not just for looks. That is the edge of chaos. It's the razor-thin line separating order from total instability. So really, the whole shape is a map of stability. Now, I want you to hold on to that idea of a boundary because it's going to be super important in a second. All right, you got that boundary idea locked in? Good. Let's put the math on the back burner for a minute and switch gears to some really cutting-edge physics. So there's this new idea called dynamic vacuum field theory, DVFT for short. And it basically says that empty space isn't empty at all, not even close. It's actually this dynamic, complex, energetic field that can have different states. Sometimes it's stable, other times, not so much. And get this, DFFT says that if you have these three specific ingredients, a complex field, some nonlinearity where the field can interact with itself, and disturbances that can ripple across all different scales, well then, fractal structures aren't just a possibility. They're pretty much what you'd expect to see. It's a natural outcome. Okay, so how in the world do we connect a mathematical fractal to the actual physics of empty space? Are we saying the universe is like a giant computer crunching the Mandelbrot equation? What's the deal? No, not at all. And this is a really important point. This isn't a literal map. We're using the Mandelbrot set as a perfect toy model, an analogy. It's a way for us to get our heads around the main idea of this pretty complex theory. And this is where the analogy gets really cool. Every piece of that simple Mandelbrot equation has a direct counterpart in the physics of the vacuum. That number z that we kept plugging back in, that's like the local state of the vacuum field. The parameter c that we started with, that's like some local force, from mass or energy. And the results, a bounded, stable result in the math, is just like a stable, coherent vacuum in the physics. And an unbounded, chaotic result, that's like a vacuum that's breaking down and forming structures, or defects. So, let's bring it all home. Remember that fractal boundary in the math, the one between stable and chaotic? Well, DVFT says the vacuum of space has its own version of that, a critical boundary. And that is the line between a smooth, boring vacuum and a vacuum that starts to form all the stuff we see. Galaxies, stars, everything. So why should you care? What's the big deal? Well, because that boundary, that edge of chaos, might be exactly where everything we see in the universe actually comes from. We're talking galaxies, galaxy clusters, the whole cosmic web. To get a little more specific, DVFT has something called the morphology control parameter. I know, it's a mouthful, but you can just think of it as a cosmic control knob. It dials in how stiff or how relaxed the vacuum field is in a particular patch of space. And check this out. Depending on how that knob is set, the theory predicts the different kinds of galaxies we see out there. If you turn it up high, the vacuum is stable, and you get these nice, smooth disk galaxies. But if you set it right near that critical point, that edge of chaos, that's where you get the really complex, beautiful spiral galaxies. And if you turn it way down, the vacuum is full of defects, and you get clumpy, irregular galaxies. It all seems to line up. And this idea doesn't just work for single galaxies. It scales all the way up. It gives us a whole new way to think about that huge filament-like structure of the cosmic web. In this theory, those filaments are basically lines of defects in the vacuum. The galaxy clusters, that's just where those defect lines cross. And those giant empty voids in space, those are simply the stable, relaxed parts of the vacuum. But look, a cool story is one thing. For a theory to be actual science, it can't just be a neat idea. It has to make real predictions, stuff we can point our telescopes at and test. And that's exactly what DVFT does. It's not just a cool thought experiment. It lays out a clear, testable program for astronomers. It makes specific predictions about the statistics of how galaxies are arranged, things we can actually go out and measure to see if the theory holds water or not. So this leaves us with a pretty mind-blowing final thought. What if this is right? If a theory like this pans out, it would mean that the incredible, complex structure of our universe, everything from the spiral arms in a galaxy to the vast cosmic web, isn't random at all. It's the result of a delicate cosmic balancing act, happening right on that infinitely complex, fractal boundary between simple order and total chaos.